Hello everyone, my name is Fabrizio and today I will tell you about quantum one-time programs. Just for the sake of statistics, how many of you are familiar with post-quantum cryptography or know about this? Perfect. This talk is not about that. This is not about making our cryptography, classical cryptography secure. It's about honest to God quantum infrastructure used in crypto. So okay. So yeah, in this talk, basically, I will describe increasingly more complex ways of playing with quantum infrastructure in Web3. The main ingredients we will rely on are trusted execution enclaves, which are quite a famous topic in Web3 cryptography at the moment, and QKD infrastructure, which is the basically most consumer-ready quantum infrastructure that we have today. Now, TEs, there is a lot of fuss around TEs. Some people say they are actually secure. Other people say, well, actually, they are not as secure as we would like them to be. But the point is that at the interplay between quantum and TEs, we can harden the security model of TEs, basically. Okay, so as a software, we'll basically rely on T-Rust, which is a Rust library that we developed to do conjugate coding on TEs. I will go through that in a second. That's the link if you want to play with it. Yeah, so let's start with a recap. So what is a one-time program? As the name says, it's a program that can be used only once. They are useful for a lot of things, especially in finance. You can imagine a quantum one-time program as a program, for instance, encapsulates some debt, and then you can use it only once to redeem the debt. And since you cannot copy a one-time program by definition, you could really treat it as a resource and trade it around. Now, one-time programs are provably impossible, both in the quantum and in the classical model. They usually require some form of trusted hardware to be implemented. And this is why we also have TEs in the mix. Obviously, the name of the game is trying to use TEs as little as possible to make this work. Okay, so the quantum thing that we are using is conjugate coding. To go through that, I'll very quickly go through what quantum is, quantum computing and how it works. So the most important unit in quantum computing is called a qubit, which is the quantum analogous of a bit. Now, the thing that you have to know about a qubit is that whereas a bit is usually it's literally either 0 or 1, a qubit can be any point on the surface of that sphere, which is called the Bloch sphere. So for instance, we have a qubit there that is in some state psi. Now, the interesting thing is that if someone gives you a qubit, in principle, you may not know what qubit that is. Indeed, if you yourself prepare the qubit or know how the qubit has been prepared, you can more or less know what state on the sphere you have. But if I just give you a qubit, you have no way of knowing what I gave you. And you can still operate on this thing. So for instance, you can rotate it, you can transform it, but you are kind of blind. You don't really know the state you're operating upon. How do you extract information from this? By the act of measuring the qubit. So measurement basically amounts to selecting an axis of the sphere, and then what you do is you project, the act of measurement projects the qubit on that axis. And that gives you a probability. So for instance, given that qubit psi, we know that if you measure along the 0-1 axis, psi is way more slanted towards 0 than toward 1. So it is way more likely that the outcome of this measurement will be 0 than 1. Now, and this is the interesting part, after you measure the qubit ends up collapsing on this axis. So basically, if I measure psi and I get 0, I completely destroy psi, and now I have that thing basically coinciding with the blue axis pointing upwards. So the act of measuring destroys the information forever, and this is the kind of key that we use in conjugate coding. So the idea of conjugate coding is quite simple. We want to encode 2 classical bits in 2 quantum bits in a way so that you can only recover one of these. And to do that, we just look at these 2 axes, right? And they are orthogonal. So basically, if you have either 0 or 1 on the red axis, so a quantum state that is either the North Pole or the South Pole, and then you measure along the blue axis, what you get is 50-50. It's literally unbiased. It's like flipping a coin. So basically, if I measure a state on the red axis along the blue axis, I get random noise. On the contrary, if I have, again, the North Pole, and I measure along the red axis, then I get the North Pole with certainty. It's like, it's basically completely certain that I will get 0 and not 1. So now the idea is that I encode the first bit on the red axis. So if the first classical bit is 0, it's North Pole. If it's 1, it's South Pole. And I encode the second bit on the plus-minus axis. So again, I go left if I want 0, for instance, and I go right if I want 1. Now I scramble the order of these two qubits, and I don't tell you which is which. So you see two qubits, and you don't know in principle which one has been encoded on the red axis and which one has been encoded on the blue axis. So now to extract information, what you have to do is you say, okay, I want to recover the first bit. Then you measure both qubits along the red axis, and what you get is the first bit with certainty and noise. On the contrary, if you want to measure along the other axis, you get the second bit with certainty and noise. The point is, again, that at this stage, you don't know which bit is the real bit and which bit is noise, and that's where you need the TE. The TE will basically store the original ordering and will tell you, okay, given this string that you obtain from the measurement, I know how to clean up the noise, how to distinguish the noise from the real bit. But the important thing is that the TE only knows the position of the noise. So after I measured, the information regarding the bit I didn't care about is completely destroyed. Okay, so what does TRAS do? TRAS basically just encodes this simple protocol. And the way it works is that we have a preparation phase where the preparing party prepares these qubits and sends them to the receiving party using some QKD infrastructure, so basically fiber optic that preserves polarization of light. Then there is an input phase where the person that wants to use the program gives an input to the program. And what the TE does is says, okay, given this input, I need you to perform this measurement. You have to read this bit, this bit, this bit. So you perform the measurement, you feed this string to the TE, and then there is a result phase where the TE evaluates the string and tells you, okay, I can execute this program or not. You can harden this thing further by using garbage circuits and other primitives to make it so no really important information is in the TE. In the best model that you can do, basically you can extract both the bits and so run the program as many times as you want, only if you hijack both the TE and the measurement equipment before the measurement is performed, which is a very tight window, and it's generally a good thing. Okay, now, how do we play with this thing? There are basically 3 levels of playing here. This is the $10 setup, which is basically no quantum at all. You just have a couple of ESP32. They are like $4 each, or in this case, an ESP32 and an Arduino. So what happens is that the ESP has the TE functionality on it. It's not like a super hardened thing. It's actually more of a toy, but you can encrypt the firmware, etc. And the Arduino is actually mimicking the quantum measurement outcome. So the TE here is saying, hey, can you measure the first couple of qubits on the Z basis, for instance, on the red axis? And that thing is giving you the noise and the actual numbers. So it's a simulator that you can download and play with, but it's quite nice, if you want to have a taste of quantum and you are on a budget. Okay, then there is the most interesting setup. The more interesting setup is basically using something a bit more quantum-y, which is the properties of polarization of light. So the way this works is that, remember when I showed you the conjugate coding thing? Now you can imagine that red and blue axes are 2 different ways of polarizing light, and the choice of bit is a mask. So here, basically, what I do is, for instance, I'm doing the z-axis, and I'm encoding a 1. Now I'm encoding a 0, and now I'm encoding the second bit. So I changed polarization, and I can still use the mask and do this kind of stuff. Now the measurement phase amounts to select the same polarization, the polarization screen, a polarization selector, and observing something on the screen. Now you see that, you know, if you polarize on the vertical axis vertically, you encoded 1, and I decode your ray of light using the same vertical polarization, then I get a 1. Sorry. Yeah, but if I change polarization basis, now I basically won't see anything. It will be like a very faint scramble thing. So again, you can play with this thing. There are a few problems here. Clearly, this must be an interactive protocol because you are not really storing qubits. You're just playing with light. But it still gives you a feeling. There is also another problem, that is quantum is a property of particles. So if you have a photon, that is generally quantum. But in here, we don't have a photon. We literally have a ray of light that carries billions and trillions of photons per second. So, you know, I could time this thing. This is definitely not a secure setup. I could time this thing to basically extract way more information than I'm supposed to. And this brings us to the real setup, which is this mess here. This is the 50K setup, which is generally quantum. So this is generally, you know, QKD infrastructure. You can see like some fiber optic free space collimators there. That big fat box there is a single photon laser. So it's literally a laser that just shoots one photon. And those things there to the right are single photon detectors that are really just like detecting one photon. And then you have some shutters and some things, and obviously our best friend, the oscilloscope, that is the only one that tells us if we are getting something interesting or not. And so yeah, that's basically the thing. The problem is that, you know, these single laser detectors and emitters cost an arm and a leg, and that's why this setup is so expensive. Again, feel free to play and, you know, contribute to this library, which is open source. There are plenty of examples, and yeah, let me know if you like it. I want just to conclude with an announcement. So in June 18th precisely, we will give the first demonstration of this experiment. So we will be at this villa in southern Italy, and we will actually run, you know, this quantum experiment. So, you know, if you want to come by and take a look at, you know, quantum Web3 interaction, that's probably something interesting. Yeah, that's it. I think we have still a bit of time for questions, right? Nice. Okay.
This is more like a curiosity rather than anything, but do you actually have a $50,000 setup in your lab?
Okay. Yes, unfortunately. Like our bank account is not thanking us right now, but yes, we do. Yeah. So we'll carry all this thing at the event, by the way. So from London, you know, we'll have to bring everything in a trolley, hoping that nothing breaks down.
Hi, thank you. So my question is, what breaks if the TE is broken? What breaks in the protocol?
Okay, so there are basically two ways of playing this. Or playing it with this. The first one is that your program is on the TE. In that case, if the TE breaks, the program can be extracted, and so it's not much better than what we have now. Now there is a second thing. The second thing is you encode your program in a Galbert circuit, basically. And instead of using oblivious transfer, which is basically an interactive protocol, what you do is you encode the tags of the Galbert circuit in conjugate coding. And the TE just knows how to clean those measurements from entropy. So if you have access to the TE before you measure, now you know how to measure strategically and extract both strings. But if you hijack the TE afterwards, then the strings have already collapsed. Most importantly, even if a remote attacker has access to your TE and can read the entropy encoding, they need to actively have access to your measurement device. So they need your cooperation, basically. So yeah, that's it.
Thank you for that. What are the main use cases you envision for this?
Well, especially everything like one-shot signature and one-time program. When you look at, for instance, execution delegation or stuff like that, the idea is that I could give you a program, and we know that quantum memories are becoming better and better. Now they are, they have a lifetime in the span of seconds, but they are progressing at 3 orders of magnitude per year. So hopefully within a couple of years, we will have a time span in the order of hours or hundreds of hours. And then what I can do is I give you a one-time program, I give you the string, and you are free to do whatever you want with it at zero latency in a fully non-interactive way. So yeah, those are the main applications.
It's July. The event is in July.
Yes, July.
Okay, very good. Is it June?
Oh, I'm an idiot. Oh, yes, it's in July. Yes. Otherwise, we would have travel in the past. Yeah, sorry. 1 month from now. 2 weeks from now, basically. Yeah. Okay.
I guess this is. Thank you.
Thank you.